Hello, today we are going to talk about the Wishart distribution. This distribution can be looked upon as a multivariate generalization of the chi-square distribution. We are going to discuss the properties of the Wishart distribution, which are very similar to those of the chi-square distribution, and I'll also hint on the usefulness of the Wishart distribution in testing of hypotheses. We shall first consider the univariate setup. Suppose we have a normal distribution with mean mu and variance sigma square where both the parameters are unknown. Let us assume that x1, x2 to xn forms a random sample of size n from this distribution. Then we can denote the sample mean by x bar, that is the usual notation, and the sample variance by S, which has the denominator n minus 1. We know that x bar will be normally distributed with mean mu and variance sigma square by n, and if I take n minus 1 S, that is going to be distributed as sigma square chi-square n minus 1, that is chi-square with n minus 1 degrees of freedom. Now, let us suppose that x has a p-variate normal distribution with mean vector mu and the dispersion matrix is sigma, which is positive definite, and we take a random sample of size n from it. Let the random observations be x1, x2 to xn. Then, as in the univariate case, we can define the sample mean and the sample. In this case, it won't be the variance, but it will be the variance covariance matrix. The sample mean can be denoted by x bar, and we know that the sample mean will also have a p-variate normal distribution. The mean will be mu, but the dispersion matrix is sigma by n. The sample dispersion matrix, which we generally denote by S, that is given by 1 by n minus 1, summation xi minus x bar, xi minus x bar prime or transpose. This S is an unbiased estimator of sigma, as we'll see later. Now, the distribution of n minus 1 S, which basically is the sum of squares and sum of products matrix, that is said to be Wishart P with degrees of freedom n minus 1 and scale matrix is sigma. Further, we note that x bar and S, these are independently distributed. This has also been observed in the univariate case. Now, we can look upon the Wishart distribution as a multivariate extension of the chi-square distribution. This is because, as we have noted in the multivariate case, where we are considering the p-variate normal distribution, n minus 1 S, where S denotes the variance covariance matrix, the sample variance covariance matrix in fact, then n minus 1 S has a Wishart P distribution. Now, in the univariate case, P is equal to 1. So, n minus 1 S will be distributed as Wishart 1 with degrees of freedom n minus 1 and the parameter sigma square. We know that n minus 1 S by sigma square in the univariate case, that will be distributed as chi-square n. This is the reason why the Wishart distribution is referred to as a multivariate extension of the chi-square distribution. The Wishart distribution can also be considered as a generalization of the gamma distribution. Let us come to a formal definition of the Wishart distribution. The Wishart distribution, it is a family of distributions for symmetric positive definite matrices. So, in the earlier slides, we had shown that if S be the sample dispersion matrix, then n minus 1 S has the Wishart distribution. Here, we assume that sigma is positive definite and S is also positive definite, and Obviously, S and both sigma, these are symmetric matrices. Let us consider the p-variate normal distribution with mean vectors null and dispersion matrix sigma. Let us assume that x1, x2 to xn, these are independently and identically distributed random vectors, each of which follow the p-variate normal distribution with mean vector null and dispersion matrix sigma. We define the matrix M as summation over xi into xi prime or xi transpose. Then M is said to have a Wishart P distribution with degrees of freedom n and sigma, which is called the scale matrix. Now, if we had considered the p-variate normal distribution with mean vector mu and dispersion matrix sigma, and suppose mu was known, in that case, we could define a matrix M as equal to summation xi minus mu into xi minus mu transpose. In this case, M would have also be a Wishart matrix, that is, M would have been distributed as Wishart P n sigma. In the particular case where mu is equal to null and sigma is an identity matrix, M is said to have a standard Wishart distribution. The density function of the Wishart distribution exists provided sigma is positive definite. And as I have stated earlier, the Wishart matrix M, that should be symmetric and positive definite. The density function of M will be given by Fm, which has the expression determinant m raised to the power n minus p minus 1 by 2 e to the power minus half trace sigma inverse m, and in the denominator we have 2 to the power np by 2 gamma p n by 2 into determinant sigma to the power n by 2. Here gamma p is the gamma function. Now the expectation of m comes out to be n into sigma. This shows that if we take m by n, that is going to be an unbiased estimator of the dispersion matrix sigma. We shall now look at some important properties of the Wishart distribution. Let us first consider the univariate situation. Say if we have that x1 has a chi-square distribution with n1 degrees of freedom, and x2 has a chi-square distribution with n2 degrees of freedom, and x1 and x2, these are independently distributed. Then we know that chi-square has the additivity property, that is x1 plus x2 will be distributed as chi-square with n1 plus n2 degrees of freedom. We have a similar property for the Wishart distribution. Here, if m1 is distributed as Wishart P n1 sigma, and m2 is distributed as Wishart P n2 sigma, and m1 and m2 are independently distributed, then m1 plus m2, this will be distributed as Wishart P n1 plus n2 sigma, that is degrees of freedom will be n1 plus n2 and the scale matrix is sigma. In the univariate setup, we could extend this to the case of n random variables. That is, if we have x1, x2 to xn independently distributed, where xi is distributed as chi-square with ni degrees of freedom, then summation xi would be distributed as chi-square with summation ni degrees of freedom. In the case of Wishart distribution too, we have that if mi is distributed as Wishart P ni sigma for I running from 1 to n, and these mi's are all independently distributed, then summation mi will also follow a Wishart P distribution with degrees of freedom summation ni and scale matrix sigma. Again, in the univariate setup, we have that if x1 and x2 are independently distributed, and it is known that x1 plus x2 is distributed as chi-square with n1 plus n2 degrees of freedom, and x2 is known to be distributed as chi-square with n2 degrees of freedom, then x1 will be distributed as chi-square with n1 degrees of freedom. Similarly, in this multivariate setup, we have that if m1 and m2 be independently distributed, and suppose m1 plus m2 is known to be distributed as Wishart P with degrees of freedom n1 plus n2 and scale matrix sigma, and m2 is also known to have the Wishart P n2 sigma distribution, then m1 will be distributed as Wishart P with n1 degrees of freedom and scale matrix sigma. Now suppose M is distributed as Wishart P n sigma and C is any real matrix of order m into P. Then CMC prime, this is distributed as Wishart M with degrees of freedom n and scale matrix C sigma C prime. In the particular case where m is equal to 1, C becomes a vector of order 1 into P. In that case, CMC prime has the distribution Wishart 1, and the scale matrix in this case is C sigma C prime, which is a scalar. Provided that C sigma C prime is not equal to 0, we then have that CMC prime divided by C sigma C prime will be distributed as chi-square with n degrees of freedom. This is mainly because of the Wishart distribution reducing to the chi-square distribution when m is equal to 1, that is when we consider Wishart 1. Another important property is that if m has a Wishart P n sigma distribution and A be any 1 by P real vector such that n is greater than P minus 1, then A sigma inverse A prime by A m inverse A prime, that will be distributed as chi-square with n minus P plus 1 degrees of freedom. Now this property holds for any deterministic A. Therefore, it will also hold for any random A provided the distribution of A is independent of M. Now let's come to the uses of the Wishart distribution. We find that if we have a multivariate normal distribution and we consider the sample variance covariance matrix based on a random sample taken from the distribution, then the distribution of the variance covariance matrix is related to the Wishart distribution. In addition, many different sum of squares and product matrices, they also have the Wishart distributions. Let us consider this example. Suppose X is a bivariate normal vector. It has mean vector 0 and the covariance matrix is given by sigma, whose components are, the diagonal components are 1 and 2 and the off diagonal component is 0.5. Now, instead of generating sample observations from the distribution of X, we can use the Wishart distribution to generate a sample variance covariance matrix. There is some further use of the Wishart distribution. In Bayesian analysis, the Wishart distribution is used as the conjugate prior of the inverse variance covariance matrix of a multivariate normal random vector. The Wishart distribution also has applicability in testing of hypothesis. Let us suppose that M1 and M2 are two independently distributed Wishart matrices where M1 is distributed as Wishart P N1 sigma and M2 is distributed as Wishart P N2 sigma. And suppose N1 is greater than or equal to P. Then lambda defined as determinant of M1 by determinant of M1 plus M2 defines Wilks lambda, and this has the Wilks distribution with parameters P, N1 and N2. Now what is this Wilks lambda distribution? Well, Wilks lambda distribution is a probability distribution and it is used in multivariate hypothesis testing, especially with regard to the likelihood ratio test and multivariate analysis of variance. So as we see that in these testing problems, the Wishart distribution has a role to play. Again, suppose we have a random sample x1, x2 to xn from the p-variate normal distribution with mean mu and dispersion matrix sigma. As before, let us denote by x bar the sample mean vector and S be the sample variance covariance matrix. Suppose we define t square as n into x bar minus mu prime S inverse x bar minus mu. Then this is found to have a distribution which is seen as the distribution of n minus 1 p by n minus p f, that is central f, with degrees of freedom p and n minus p. Now this is called Hotelling t-square and this is used in testing regarding the mean vector mu. That is, it is used, say, if we want to test a hypothesis h naught, mu equal to some mu naught. It will also be used for testing hypothesis like A into mu equal to null, where A is a given matrix. So Wishart distribution, which comes as distribution of S, of course, with a constant, is useful in this case too. This is a reference to the Wishart distribution. So today we have studied the Wishart distribution, which, as I have said earlier, can be looked upon as a multivariate generalization of the chi-square distribution. We have looked at the important properties of the distribution, that is the Wishart distribution, and we have also briefly talked about its usefulness in hypothesis testing.